Section 9.2, Matrices and Simultaneous Equations. So by the end of this video, you should be able to take simultaneous equations and represent them as matrices. You should be able to use matrices to solve simultaneous equations. Use the determinant of a matrix to work out if a set of simultaneous equations has one solution, one unique solution. And you should be able to create a set of simultaneous equations from a real life problem. Okay, let's first of all get to this area here. If I have matrix A multiplied by matrix X and the answer is B, then matrix X will be equal to the inverse of A. So whenever you see to the power of -1, that means inverse matrix multiplied by B. So AX equals B, then I can say that matrix X will equal the inverse of A multiplied by B. And this is really handy for simultaneous equations. So if we think of the variables X and Y, coefficients A, B, C, D, so they're just the numbers in front of those variables, and then E and F as being the answers or the constants, then we can make use of the connection of that and this here. It's much better to see in a real good example. So equation 1 is 2x plus 3y equaling 13, and equation 2 is 5x plus 2y equaling 16. So what I do is I take what I call my coefficient matrix. So these are the numbers in front of the variables. So 2, 3, 5, and 2. So that's my coefficient matrix. If I multiply it by the variable matrix, so I've got x, y, and then that will equal what I'm calling my answer matrix, so 13, 16. So I now have this set up in that terms of AX equaling B. So matrix A multiplied by matrix X equals B. So that's matrix B, matrix X, matrix A. I know that my matrix X will equal the inverse of A multiplied by B. So the inverse of A, so I recognise A is 2, 3, 5, 2. There it is there. And if it's the inverse, I just raise it to the power of -1. And then I multiply that by my answer matrix, which is 13, 16. And that will give me my variable matrix XY. So I evaluate that using my CAS, and I'll get this XY matrix, my variable matrix, is equal to this matrix here. So in other words, just equating same positions, X is equal to 2 and Y is equal to 3. Whenever you're providing your solutions, you can't just leave it in that matrix format. So common mistake by students in an exam 2 situation is just to write this equaling that, and you'll be marked incorrect. You need to take it out of the matrices. So X is equal to 2 and Y is equal to 3. The other key point here is that when you have your sets of simultaneous equations, make sure that you have it in that exact same format. So you have XY, then the next equation needs to be also XY. And then you've got 13, 16, and so on. So getting the coefficient matrix is pretty easy, so that's it there. But of course, when you write down your variable matrix, you need to also make sure that you're doing in the same order. So we're going X then Y, so we need to go X then Y going down. Okay, so this little section of 9.2 is probably a little bit heavy as far as theory is concerned, but just hang in there. We'll just take a look back here where we found out one unique solution for the set of simultaneous equations. We found that when X equals 2 and Y equals 3, both the first equation given, this one here, and the second equation would be true. And that gives us one unique solution. Now, what we're going to explore is situations where we don't have one unique solution to our sets of simultaneous equations. And I want you to begin by just making a little bit of a point, perhaps somewhere up here, that we'll have one unique solution whenever the determinant of a matrix does not equal 0. And graphically, that will be shown as two lines that intersect once. So two straight lines that intersect once and only once. And the point of intersection is in fact the solution. So just draw a little sketch of that. Okay, now let's look at this graph here on the right hand side. We have two parallel lines. There's equation 1 and here is equation 2. At no stage will those two lines intersect. Therefore, this will not have one unique solution. This will have no solutions. There is no value of x and y, no point in this Cartesian plane that will satisfy equation 1, and then simultaneously, that is at the same time, it will satisfy equation 2. So this has no solutions. If we took those two equations and set themselves as a matrix equation, if we took the coefficient matrix and worked out the determinant of that, then that determinant would equal 0. And we'll see that a little bit later on. Here we have a second situation. Again, we have two equations, but in fact, they are the same equation. So if we've got 2x minus y equaling 5, if we double everything there, we'll get 4x minus 2y equaling 10. So whilst we can write them down as two different equations, they are in fact the same equation. And if you were to graph those separately, you would see that they would form exactly the same line. Now in this situation, there's not one unique solution, not one particular point x, y that satisfies both equations at the same time. There's an infinite number of solutions that are possible. So every single point along this line satisfies both equation 1 and equation 2. So in this situation, there are infinitely many solutions. And if we express these two equations as matrix equations, then if we took the coefficient matrix and worked out its determinant, we'd see that the determinant is equal to 0. So that's our two key bits of knowledge here. All right, so let's look at this example. I think it's a lot clearer. For each pair of simultaneous equations, use matrices to find the value of E for which the equation do not have a unique solution. So if we do not have a unique solution, the determinant of the coefficient matrix will equal 0. Let's look at A. We've got the coefficients are 7, 5, an unknown E, and 5. So we put that in the coefficient matrix. The variables are x, y, and they've listed in the same order, so that's good. So we list that variable matrix x, y, and that provides us with answers 12 and 11, and that's it there. So what we're saying is that if we calculate the determinant of this matrix here, the coefficient matrix, if it's equal to 0, then we will not have a unique solution. So to calculate the determinant, it's that diagonal times together, so 7 times 5, minus this diagonal times together, so E times 5. So 7 times 5 minus E times 5, and that's shown here. Now, the E is unknown. We need to work it out so we do not have one unique solution. So if we set the determinant to equal 0, then we'll have 35 minus 5 lots of E. And then we can just solve for E. And of course, just use your CAS. So menu algebra solve and put in this equation here, solving for E, and we'll see we'll have a 7. So let's look at now at the second set of simultaneous equations, and here we've got an unknown E. Again, let's create the coefficient matrix. So 11, -3, 22, and E. We've got the variable matrix x, y, and our answer matrix -9, 2 here. If we do not have one unique solution, then the determinant of this coefficient matrix will equal 0. So I'll have a 0 here, and that will equal 11 times E minus 22 times -3. That's shown here. Please note that you can just set it up here. If you have a 0 equaling all of that, including the brackets, you can put that line straight into your CAS calculator to work out the unknown E. But by hand, we've just tidied things up here. We've got 11E plus 66. And so we finally get to this equation. 0 equals 11 lots of an unknown E plus 66. We need to solve for E. and we'll get E equaling -6. So if in here we have -6, then what we'll have is a situation where we don't have a unique solution. So we either have no solutions at all that satisfy both equations, or we have an infinite number of solutions that satisfy the equations, and you can refer back to those graphs. Okay, so this page here shows us how to make use of our CAS calculator and with matrices and simultaneous equations. To be honest with you, I'm not a big fan of the way that we're shown how to do it on this particular page, and I'll show you why shortly. But if we have ourselves a set of simultaneous equations, notice here for this second equation, there's no value in for y. It's important that we put in a 0 or 0 lots of y in this equation when we deal with matrices. So here's our coefficient matrix. So these are just the numbers in front of the variables, x, y, and z. And here where we've got a missing y, I place in a 0. I have my variable matrix, and it's in the order x, y, z, because these variables are all listed in x, y, z. If they're not, you need to change things around. And there's my answer matrix. I know that my variable matrix will equal the inverse of this matrix, the coefficient matrix, multiplied by the answer matrix. So rather than using copying and pasting, rather than defining each of these matrices as A, B, and writing all this out, what I suggest you do is use copy and paste. And I'll show you that with the example that's just below here. So here we have example 3, and we've got ourselves a factory that has 3 robots that assemble 3 different types of computer models. And the computer models are A, B, and C. And the big assumption here is that each robot performs as efficiently as each other. So no particular robot is better at assembling any type of computer than any other robot. Now, what we're interested in working out is how long it takes a robot to assemble model A, how long it takes any of the robots to assemble model B, and how long it takes any of the robots to assemble model C. So these are 3 unknowns. Now, if we've got 3 unknowns with simultaneous equations, we need 3 facts, and here are the 3 facts. So robot 1 assembles 3 lots of model A and 2 lots of model B and 5 lots of model C in 113 minutes. So if I have A being the amount of minutes it takes to assemble computer model A, and little b as being the number of minutes it takes to assemble one computer model B, and C, of course, being the amount of minutes it takes to assemble one computer model C, if I use that kind of setup for my simultaneous equations, then I can come up with, from that first fact, 3 lots of A plus 2 lots of B plus 5 lots of C will equal 113. So that's from this first fact. Second fact, robot 2 assembles 1 model A and 3 model Bs in 56 minutes. So here we have 1 lot of A plus 3B equals 56. And then finally, the last fact, robot 3 assembles 2 model Bs plus 1 model C in 40 minutes. So there are our 3 facts. We're able to develop 3 equations, and there's 3 unknowns, little a, little b, and little c. And we're going to put that set of simultaneous equations into a matrix format and then solve for a, b, and c. You can see we have an unknown a here and we have an unknown c there, so we're going to put in zeros. So first equation, and second, and third. So here we have our coefficient matrix. So these are just the numbers in front of the variables for each of those equations, equation 1, equation 2, equation 3. I have my variable matrix, and it's in that same order, so A, B, C, A, B, C, and there's my answer matrix. Now I want to solve it for A, B, and C. So I want to get matrix X. So matrix X is going to be equal to the inverse of the coefficient matrix. So that's it shown just here. So it's that to the power of negative 1, multiplied by the answer matrix, so 113, 56, 40. That's it there. Again, I do this calculation on my CAS, and I have A equaling 11, B equaling 15, C equaling 10. And of course, we can't just simply leave it like so. We need to take our answers out of the matrices. So it takes a robot, any of the 3 robots, it doesn't matter, 11 minutes to assemble model A computer. It takes 15 minutes to assemble the model B computer, and it takes 10 minutes to assemble the model C computer. Okay, so on the previous page, I pretty much bagged out how the steps showed to make use of the CAS calculator, because in those steps they wanted you to define each of the matrices, and I find that very time consuming and confusing. So instead I encourage you to put the matrices directly in, or make use of copy and paste if you've already put those matrices in beforehand. So if we go, and you can see our solutions are here, and you can understand how we got the time it took for model A, B and C, but let's see what we did on the CAS. So whilst this, here's our original set of simultaneous equations that we developed. In matrix format, we could show it like so. We need to solve for A, B and C, so we realised that basically what we're doing is taking the coefficient matrix, finding its inverse, so i.e. raising it to the power of negative 1, and then multiplying that by the answer matrix, and then that would give us what each of the variables were equal to. And that's shown in this relationship here. So putting it into our CAS, what I need to do first of all is just go to my matrix template, so clicking on that, and you can see I've got some of the different dimensions. I just want a standard 3x3, and my values I need to put in, or my coefficients, are 3, 2, 5, and then 1, 3, 0, and then 0, 2, 1. Oops. Now that there, as it is my coefficient matrix. Now I want to find the inverse of that, so I'm just going to raise that to the power of negative 1. So now that's the inverse of the coefficient matrix, and I multiply that by my answer matrix. So I'm going to bring up that matrix, and that is going to be 3 rows by 1 column. Go OK, and then put in the values, so 113, then we had 56 and 40. Hit enter, and there's what each of the variables are. So A is 11, B is 15, and C is 10.